See, good morning and good afternoon. Today we are going to just add in our module 4 another topic called the product of inertia. If you look at the second moment of area of the section is not one single value. It is a tensor. If you look at component is represented by XYZ axis, you would have your section property IXX, IYY, IZZ. Also, you can have the product of inertias. What is that called? IXY or IXZ or IYZ and so on. So what are this product of inertia? What are their significance is what we will understand in today's class, right? So let me share my Active Inspire board. So hope all of you are able to see this board. Essentially, this is lecture number 30 and 31, what we were doing in the last class. So we just have revisited second moment of area, or otherwise called the area moment of inertia. And we were additionally defined what is called the radius of gyration in the slide that you could see, and also apply parallel axis theorem. So it is one of the transfer theorem, which is quite useful theorem. If I know for a standard section about its centroidal axis, the moment of inertia value, then I can find out any parallel axis what is the section area moment of inertia. So that is what is advantage or application of transfer theorem called parallel axis theorem. You could also apply another theorem called perpendicular axis theorem. So that would give you what is the area moment of inertia, or that's called the polar moment of inertia of the section with respect to the axis perpendicular to the section. So if I have IXG and IYG, I can find out an axis area moment of inertia, polar moment of inertia about the axis ZG by applying perpendicular axis theorem. So that theorem state it is simply summation of IXG plus IYG. So this is all what we have seen in the last class, and then we have listed down the standard formulas for this section, standard sections with respect to their centroidal axis. So if you know that, I can find out for any other axis parallel to the centroidal axis, right? Or if I know for any given section about an axis other than centroidal axis, its moment of inertia, it is easy to calculate what would be about the centroidal axis using parallel axis theorem. Right? In both the way one can use that theorem. And we have taken this interesting problem where it appears only simple section on circle, and where this right angle triangle is removed from there. It is only description of a circle area minus a triangle area, but you could see that more involvement of actually finding the parallel distances between the reference axis and the centroidal axis. So this is what we were doing it in the last class. I hope you have done this problem. And finally, I was telling you this values to calculate and find this. I think you could have done that. So now I am sure that you have understood first moment of area, second moment of area, and you would be able to solve for a given composite section to finding out centroidal axis, and about the centroidal axis we are asked to find out area moment of inertia. You can easily calculate them. So this is very much essential for CAT 2 examination point of view. And today we are going to add with this topic and another interesting definition called the product of inertia of the section. So let us look at what it is. So this is lecture number 32. And you have today's date 17/04/2021. Product of inertia. So this definition, the term itself says what is it. Mathematically you can define it is IXY equal to integral product of the coordinates XY dA. So this is definition of product of inertia. This is definition of product of inertia. So let us again look at our generic case. of representation of a section area, which is an arbitrary section area. And I have now CG location of this centroidal location is somewhere here. So I have my centroidal axis as well. This is my XG axis and YG axis. And I have now an elemental area defined here, which is dA. So this dA is given by now x comma y with respect to centroidal axis. X comma y with respect to centroidal axis. Whereas the centroidal axis are defined with respect to the given reference OX, OY axis by x bar and y bar. These distances, right? So this is how we just consider a generic case of a section, and we were able to prove parallel axis theorem. So now let us go for a product of inertia definition. So now this IXY, this XY refer to this axis X and Y axis. So how do I get that integral? So this dA distance from, do not misunderstand this XY, what is written here. This XY is the coordinate of the elemental area with respect to XY axis. So that would be X plus X bar into Y plus Y bar dA, right? So this is what is my IXY. So now see, if I do multiply this, it is XY dA plus integral x bar y dA plus integral x y bar dA plus x bar y bar dA, right? So now you see here xy dA is what is that section product of inertia with respect to centroidal axis xg yg axis, because x and y coordinate here in this x is from this axis, y is from this axis. So this product into dA is what is actually product of inertia about the centroidal axis. So that's going to be I would write that as this, okay. I xg yg plus, look at here, x bar into y dA. So x bar is constant for this section to define its centroid. If I take out, it is integral y dA. What is integral y dA? It is first moment about its centroidal axis. So first moment of a section about centroidal axis is 0. So this term is going to be 0. Similarly, you see y bar, if I take out, it is integral x dA, which is its first moment about centroidal vertical axis. So this term also is going to be 0. And I have here x bar, y bar taken out, which are constant, and integral dA is total area, and this is what is IXY. So what is that you understand from this simple derivation is what is proof for parallel axis theorem applicable in product of inertia definition also. So parallel axis theorem, axis theorem holds good for product of inertia as well, right? So this is what you should understand. So what do you mean by that? If I know the product of inertia of the section about its centroidal axis, then I can find any axis set parallel to the centroidal axis, right? Simply by parallel axis theorem. So that's what you understand here. So let us look at a simple section, very standard section, rectangular section. So I have, this is my rectangle. This is x-axis, y-axis, reference axis, and this is depth D and width B. So I know the area of this rectangular section is B times D, right? And I know by observation itself, I can also apply first moment principle and get this. But by observation itself, because of axis of symmetry, they are centroidal axis. This is XG axis, and this is YG axis. So they are located at a distance of x bar and at a distance of y bar. By the way, what is x bar? Is B by 2, What is y bar is d by 2 from this O, right? So this you have. So now what is my product of inertia definition, right? So product of inertia is Ixy, that's equal to integral xy dA. So this I have to do. So let me just find out this for this rectangle. So let me take this rectangle. This is x, y, and this is B and this is D. So let me consider an elemental strip. So maybe I'll consider an vertical elemental strip. This is at a distance x of dx. This strip. Let's consider. Now, what is dA of this? dA of this is dx into d. So d into dx is what is dA. So now, what is its centroidal axis? It is somewhere here. Its coordinate is here because it's a rectangular strip. So this is here. So I have here my x bar and y bar. So what is for this element? X bar is x itself. What is y bar? Is d by 2. Right? Y bar is d by 2. Now, how do you get this? This is integral dIxy. So whatever that I have it for my element product of inertia, if I integrate that over this distance 0 to x, 0 to b, I would get my product of inertia. That is the meaning. So I can have xy dA, or I can have it like that. So in this xy dA refer to the coordinate. I am not taking a small element like that and putting it. Rather, I consider an elemental strip, and I have my dA defined, and the centroid of this element if I have, and if I know for this elemental strip about the xy axis product of inertia, I will be able to get it for an entire section. So how do I get that? Now that is why it is elemental product of inertia dIxy written. So dIxy is this for this element about this axis. You need to understand this product of inertia about centroidal axis is going to be 0 in this case, because these axes are called the principal axis. You'll understand what are principal axis in a while, right? Principal centroidal axis. So about that, that's going to be 0. Why? Because x bar, y bar to define with respect to xg, yg is 0. So what does that you understand here is Ixg, yg product of inertia about central axis is 0 is because it is integral x y dA. So x and y for this Ixg is 0 with respect to its own axis. So this is going to be 0. So if we understand that, for this now section about its centroidal axis it is 0. So how do I write this is like this: dIxg yg plus x bar y bar into integral dA is what is by applying parallel axis theorem. So this is going to be 0 for an element about this centroidal axis because the elemental centroidal axis is somewhere here, right? So about this for this elemental thing, this is going to be 0, and I will have only this. So that's going to be x bar value is x, y bar value is d by 2, and dA. So dA is d into dx, and this all to be integrated from 0 to b. So if I do this, carry out this integration, d is constant here, which is depth of the section. So d square, let me take it out. By 2, I'll take it out. Integral x dx varies from 0 to b. So if I do so, what is that I'll have? Is d squared by 2, and this integration is going to be x squared by 2, 0 to b. That's going to be b squared d squared by 2. Sorry, by 4, right? b square d squared by 4. Is what is IXY of my rectangular section. Right, so like that you can get what is the product of inertia of your rectangular section. Just a minute, I'll get an example problem. Okay. So I leave it to you to work out for other section as a homework, which is triangular section. So let us take now a triangular section. This is B and this is H. So here the difference is, if I consider an elemental strip, so this strip is a rectangular strip. The product of inertia about its own centroidal axis is 0. So I have to get this centroid x and y distance. So x distance as well as y distance is going to be varying. So you have to carefully account them. And then you would be able to derive what is the IXY about this XY axis. So if we have that, then I can find out, of course, what is there for this centroidal axis. If this is my XG, YG axis, I can find this IXG, YG as IXY minus X bar, Y bar into area. So the other way I can find this expression. So I leave it to you to work out. So now what is important thing is, understand by observation of axis of symmetry, right? If I have my rectangular section, so here I have my axis of symmetry. If I have my circular section, I have my axis of symmetry that gives my centroid. So that these axes are centroidal axis, XG, YG axis, XG, YG axis. So the product of inertia about the centroidal axis is 0. Why it is so? Look at now, I have 4 identical areas spread in this 4 quadrants, right? So if I take here this point x comma y, I would have a corresponding coordinate here. This is x comma y, and here it is minus x comma minus y, and here it is minus x comma y, and in this case it is plus x comma minus y. So these are this coordinate. If I take corner points, where it is this point, I have it like that. So this product here, it's positive, this is positive, whereas the product of coordinate here and here, you look at, it is going to be minus x, this is minus and this is minus, this product of this coordinate, right? And total sum of this, all products are 0. That is why you have product of inertia 0 about the centroidal axis. And product of inertia 0 about an axis set, that axis set is called the principal axis. So principal axis is the one where you have product of inertia is 0. So for this chosen rectangular section, IXG, YG is 0. So the centroidal axis are also called as principal or centroidal axis. So what do you mean by principal centroidal axis? I will have one axis about which I will have maximum area moment of inertia, and about another axis I will have minimum moment of inertia. That is the meaning of that. So any section orientation in your structure should be such that the orientation of the section should ensure that would offer a maximum area moment of inertia with respect to one axis, right? So that is very important. So for that purpose, you require to locate section orientation, and the axes are going to be principal axis, and principal axis are the axis 1, when the product of inertia is 0, right? So that you should understand. So for this two sections drawn, you have these axes are not only called centroidal axis, also called principal axis. So now the question is, if all principal axes are going to be a centroidal axis, if that is the question, you should say no. All centroidal axes can be principal axis if they are axis of symmetry. If they are not an axis of symmetry, then it is not so. For example, you look at a triangular section. This triangular section, you have no axis of symmetry. You have your XC, XG and YG axis. This is your centroid here, centroidal axis. Now you see the spread of this area in first quadrant is small, second quadrant is trapezium, this quadrant it is a square, and in this quadrant it is another trapezium. So the areas are uneven. So you would have your product of inertia about XG-YG axis, you would have about XY axis as well, right? So your IXY in this case about the XY axis is going to have some positive value. Whereas your IXG, YG, if you look at the value, what you get would be negative value. Why that would be negative value? You see the area spread in the second quadrant and the area spread in first and third quadrant. This happens to be more than that. So you would have a negative value of your product of inertia. Unlike area moment of inertia, product of inertia can have negative value or can have positive value, right? So if I have my rectangle represented in first quadrant like this, XY, so my IXY is positive. If the same rectangle is represented in second quadrant like this is my x-axis, y-axis is negative axis. So now I have here any coordinate is negative x and positive y. So IXY value is going to be a negative value here, negative value, right? So this is what you should understand. Product of inertia can be positive, negative, or 0. When it is 0 about an axis set, then that axis set is called a principal axis. And the principal axis can happen to be a centroidal principal axis of these sections. You can also have a principal axis for a rectangular section in this way. If I have my rectangular section represented by this x and y axis, I can also have a principal axis other than centroidal axis. Other than centroidal axis. That means what? I can have now about Ix and Iy, what are the value? I know that Ix, what is my value? If this is B and this is D, this is Ixg plus dy square into area. So it is BD cube by 12 plus D by 2 square into BD. So what is that I have is BD cube by 3 is what is my Ix. And what is my Iy? In the other way, Iyg plus the dx square into A. So that's going to be B cube D by 12 plus B by 2 square into BD. That's going to be B cube D by 3. So I have these formulas. So now you see again, I cannot have this value is the greatest value for this section about x-axis or about y-axis. So if I have my section like this, solid section, and my reference is here, right? My support is here at this edge, then I am still not having an appropriate orientation of my section in the system, right? So I should have my orientation of the section such that I would be able to have my maximum and minimum value of my area moment of inertia. So I should be able to locate my principal axis. So that axis to get, let us just find out now what would be my area moment of inertia about x dash axis and y dash axis. if this axis is rotated by an angle theta. So I rotate this angle axis by angle theta, then I just have to find now about this, right? So Ix I have BDQ by 3, Iy I have it like this. Or I know the definition of Ix. Ix is integral y squared dA. Iy is integral x squared dA. But now what is my Ix dash and what is my Iy dash? And I know here my Ixy is simply integral xy dA, which we just derived some time back. But what is my Ix dash y dash? So if I have my Ix dash y dash value, and if I make that is equal to 0, I would get an orientation of this axis set which would correspond to my principal axis. That is the idea. So now how do you find this Ix dash, Iy dash and Ix dash y dash about the new axis set for the same rectangular section is what I'm going to explain you. Is that clear so far what I explained? Anybody has any doubt? Anybody has got any doubt? Divyanshi, you have any doubt? Venkat Satvik?
No, sir.
No doubt.
No doubt, right? So you understand what is the difference between area moment of inertia and product of inertia. And that role is there going to be now. If I have to find out Ix dash, I have to account the product of inertia also. That is going to be influenced by the product of inertia, Ixy as well, right? Iy dash to find, I would see that that is also going to be dictated by Ixy of the section. So that simple derivation is what we are going to look at now. So let me once again take an arbitrary section. And this arbitrary section, I have now an axis set x, y with respect to this point O. And also I have a new axis set x dash, y dash, which is obtained by rotating this axis by theta degrees. So this is my new axis set. So now let me consider an elemental area. This elemental area. So this elemental area is now located with respect to my x and y axis. I would say this is my x length and this is my y length. Now with respect to new x dash y dash axis, where distances are represented by x dash and y dash. So let me put that. So from here I just draw a line parallel to x dash axis, and that's going to be my x dash. And from here I will draw a line parallel to y dash axis, and that would be my y dash, right? So x dash y dash with respect to tilted axis set, x comma y coordinate is with respect to horizontal and vertical axis set. So if this is so, I can define now here what is my x dash and y dash. Let me just define what is my x dash. So this x dash can be explained in terms of x and y coordinate. So for that, this simple geometry that we have to understand. So what is that geometry is this. So you see that if I drop from here a perpendicular that is parallel to y dash axis, right? This perpendicular like this. And that angle is again going to be theta. This, if I draw perpendicular, which is parallel to this y dash axis, this angle is theta. This angle is theta. This angle is theta. If this angle is theta, now I can write my x dash as x cos theta plus y sin theta. X cos theta and y sin theta. See, look at now x dash. So how do I write? If this angle is theta, this angle is theta, right? This angle is theta. So x cos theta. So if I project this, x cos theta and plus this. So that would be what? This is y and this angle is theta, opposite to this y sine theta. That is how it comes. And what is my y dash? So y dash is this distance. That would be, this angle is theta and this is now y. So y cos theta minus x sine theta. So y cos theta minus x sine theta, right? So this is how I can represent my new coordinate x dash y dash of my elemental area of this arbitrary section with respect to new axis set x dash y dash. So if I have that, now I know mathematical definition of area moment of inertia and product of inertia. So let me work out for Ix dash. So that's going to be integral y dash square dA. So that's going to be integral y dash is y cos theta minus x sine theta into dA. Right? So in this square. So now this a minus b whole square. So I can split this as y squared cos square theta plus x squared sin square theta minus 2xy cos theta sin theta. So if I do that and take cos square theta out, so this is going to be integral y squared dA, and x squared out, sorry, sin squared out, sin square theta out. That's going to be integral x squared dA, and 2xy sin theta cos theta into dA. So in that, if I take 2 cos theta, so minus 2 cos theta sin theta out, integral xy dA I'll get, right? So now you know definition of y square dA is Ix, integral x square dA is Iy, integral xy dA is Ixy. So I can rewrite this as, this integral is Ix, so Ix cos square theta plus Iy sin square theta minus 2 cos theta sin theta into Ixy, right? So this again can be written by trigonometric relation, convenient trigonometric relation, like this. So you know 2 sin theta cos theta is sin 2 theta. So I can rewrite this as Ix cos square theta plus Iy sin square theta minus sin 2 theta, Ixy sin 2 theta. Ixy sin 2 theta. So that's equation number 1, which is Ix dash. So similarly, I can get now what is my Iy dash. So you can parallelly work out along with me and verify what I'm doing is correct. Iy dash is integral x dash square dA. So integral x dash is what? X cos theta plus y sin theta into dA. So if I work out this a similar way, I will have cos square theta integral x squared dA plus sin square theta integral y squared dA plus 2 cos theta sin theta into xy dA. So here it's minus sign, it's plus sign. So it's going to be x square dA is Iy. Here it is Ix. So Ix sin square theta. So Ix, first I write this term. So Ix sin square theta plus Iy cos square theta. And this 2 sin theta cos theta is sin 2 theta again. So plus Ixy sin 2 theta. So this is my equation number 2. What is Iy dash? Like you have here one important relationship. What is that is? You can just add 1 and 2 and see that product of inertia terms goes off, and I have Ix commonly taken out, sin square theta plus cos square theta 1, and Iy taken out, sin square theta plus cos square theta term 1. So I have Ix dash plus Iy dash is Ix plus Iy, right? So what is this? So this is Iz dash and this is Iz. Because if you add this, that is polar moment of inertia by perpendicular axis theorem. By perpendicular axis theorem, The summation of these two is what is the area moment of inertia about z axis called the polar moment of inertia, and that is not changed, that remains same. So what is that you understand? If I have my rectangular section and if I rotate my axis set holding xy plane only tilted and z axis is not orientation is not changed, then I have my polar moment of inertia of the section about z axis is not changed, right? So Iz or Iz axis is one and the same. That's proved here. That's one thing. And then why did I have this relationship is because I want to eliminate this theta terms and then trigonometric term. Then I want to show that these are equation, parametric equation of the circle, so that we can represent the relationship between Ix, Iy, Ixy graphically by a circle called Mohr circle. So that is the idea. And similar analogous study you are going to study in your strength of material course as well, looking at principal stresses and shear stresses and normal stresses relationship, right? So you would define something called the principal planes or the one where shear stresses are zero. So you would essentially have your section orientation is changed. You would have your stress values are changing. So you will have the stress value is a combination of normal stress as well as shear stress. This is all you are going to study, analogous study. But same way the section properties now whatever you are studying, you see that when you do the next course you would see that similar kind of analysis derivations for stress and strains as well. So now continuing with this, now I had now got two equations for area moment of inertia. Now let me get it for product of inertia, Ix dash, Y dash. So what is that is going to be? It is that is X dash, Y dash into dA. So what is my X dash? It is integral X sine, X cos theta plus Y sine theta into what is my Y dash? It is Y cos theta minus X sine theta into dA. So now this product is going to be this. So I have xy cos square theta. So cos square theta, let me take it out. Cos square theta, let me take it out. So it is going to be integral xy dA plus I have here first term is this product. The second term is y squared cos theta sin theta. So cos theta sin theta, let me take it out, it's integral y squared dA, and again this minus x squared into sin theta cos theta, so it's going to be minus cos theta sin theta and in bracket x squared dA, and then I have x and y product and sin squared, so that's again minus, so minus sin square theta integral xy dA, right? So here you see I get this now, right? So what is that I'll get? I can use some additional trigonometric relation that we know, that sin 2 theta, which we have used already. Sin 2 theta is what is 2 cos theta sin theta. And you know what is cos 2 theta? So cos 2 theta is cos squared theta minus sin squared theta, or cos squared theta minus sin squared theta. Then what is cos squared theta? Cos squared theta you can write it as this way: 1 plus cos 2 theta, 1 plus cos 2 theta by 2, and sin 2 theta you can write it as, sorry, sin square theta. Sin square theta you can write it as, this is cos square theta 1 minus cos 2 theta by 2. So these trigonometric relations proofs that already you have learned in mathematics trigonometry, and you should use them. So if I use those things and I can rewrite my this equation for product of inertia as follows. So what is that? Is going to be Ix by 2 sin 2 theta. Let's look at that. Ix by 2. Ix is what? Integral y square dA. So integral y square dA is what is Ix. And y by 2 is because I will put here 2 and divide by 2. So that 2 cos theta sin theta is what is sin 2 theta. So sin 2 theta, right? So this term is taken. Next you see similarly x squared dA. So again I will multiply 2 by 2 divide by 2. So this is going to be minus Iy by 2 sin 2 theta, right? Sin 2 theta. So this term is also accounted. Now here this cos squared theta and this, so if I take this integral out, cos squared theta minus sin squared theta, what is that? It is cos 2 theta. So I can rewrite this as Ixy cos 2 theta, right? Ixy cos 2 theta. So now let me again combine this here. Sin 2 theta common, so I can take that out. So Ix minus Iy by 2 into sin 2 theta and plus Ixy cos 2 theta is what is Ix dash y dash. That's my equation number 3 for product of inertia. So now see that the moment you are having your section rotated like this, the values what we had about xy axis given by bd cube by 3 or b cube by 3 are changed now. So about ix dash, it is not only of ix iy value, also the product of inertia comes. So the moment the section orientation is changed from horizontal, or you are referring that other way by rotating the axis, the area moment of inertia values are going to be coupled. So Ix dash means I require Iy dash value, sorry, Ix, Iy, Ixy, all three are required. That's what you are witnessing now. Looking at this equation. One, you see, to calculate Ix dash, I should know for my section Ix, Iy, Ixy, as well as this angle theta. This trigonometric formula is required. So this is how you would be able to find these three values in a generic case. But now what is the understanding is graphical representation of these answers. So how do I go about doing it? So for that, I will do now this equation 1. I'm going to rewrite as Ix dash as this way. I'm going to replace my cos sin squared theta term and cos squared theta term changed. So my equation 1 Ix cos squared theta, I'm going to write Ix cos squared theta term is 1 plus cos 2 theta by 2 and plus Iy, and that sin squared theta term is 1 minus cos 2 theta by 2 minus Ixy sin theta, sin 2 theta. So look at here, I have my first expression is cos square theta and sin square theta with this trigonometric term relation I changed. So now this I can bring in the other way. So first term is Ix by 2, here Iy by 2. So I can take that term, that is Ix plus Iy by 2 out, plus second term is Ix cos 2 theta by 2, here minus Iy cos 2 theta by 2. So I can take cos 2 theta by 2 out. So this is going to be Ix minus Iy by 2 into cos 2 theta minus Ixy sin 2 theta. So I am purposely doing this so that I can eliminate this trigonometric term and I can finally deduce that can be represented as a circle, parametric equation of circle. So this is the equation number 4. So now similarly I can get my Iy dash. In Iy dash, what is that I have? Again cos square theta term and sin square theta term. Right? So see Ix sin square theta, Iy cos square theta. So these two terms I replace by this relationship, so that this equation can be rewritten as this. I would have, of course, this Ix plus Iy term here as well. Instead of plus, I would have here minus, and within bracket I will have Ix minus Iy by 2 into sin, sorry, into cos theta. See, cos 2 theta, and here instead of minus I have ixy cos 2 theta, right? Sorry, ixy sin 2 theta, sin 2 theta is my equation 5, right? So now see that if I add this again, what is that I would have? This terms goes off and this terms goes off. I get the proof of ix dash plus iy dash equal to ix plus iy, right? Adding 4 plus 5, I could again have a proof that the polar moment of inertia does not change, right? Now, how do I get my I max and I minimum? I max and I minimum to get. Let me now express this as a parametric equation of circle. So what I will do, I'll keep this trigonometric term on one side of this equation 4, and this term on the other side I'll bring in. So let me take now equation 3 and 4, equation 3 and equation 4, considering equation 3 and 4, I'm going to do this changes. What is that I'm going to do is I'm going to bring in non-trigonometric terms on one side and trigonometric term on the other side. So my equation 4 would be first ix dash minus, I bring this on this side, so that is minus ix plus iy by 2, right? On the other side I would have now ixy, ix minus iy by 2 cos 2 theta minus ixy sin 2 theta, right? So let this equation be squared on both sides. Be square on both sides. Equation 4 I take, manipulate like that, grouping trigonometric term on right hand side and non-trigonometric term on this side, and I'm squaring on both sides. You would understand why do I do that is because I want to eliminate this trigonometric term, right? So now what is my third equation? Third equation is ixy. So square the third equation also on both sides. So I would have ix dash y dash square one side, and the other side I would have what was the term here as ix and as iy by 2 into sine 2 theta plus ixy cos 2 theta whole square, right? So now you see here this term. For this I have cos 2 theta, and here I have sin 2 theta. Here this ixy sin 2 theta is ixy cos theta and plus minus. So if I square and add this trigonometric term will disappear. I would end up with simply ix minus iy by 2 whole square plus ixy square. On this side, I would have. So let me have this equation is the equation number 6. This equation is equation number 7, and adding 6 and 7, I would have this sum. So that would be ix dash minus this ix plus iy by 2. I would define as I average. So what is I average? ix plus iy by 2. Let I average is this. So I will have this this whole square plus ix dash y dash square is what is on this side. So now you again look at this equation as this way: ix dash minus
Hello.
So I had a network issue here at my home, and it's gone again. I got connected. Right. So let's continue with that. A small portion of our derivation left. I could see that there are many students left. That's fine. They can revisit this video lecture. However, I will finish then and upload this link in the MS Team. Right. So let me continue with my lecture. I hope you are able to see this screen. Right. I'll share once again. This is where we were there doing our connection loss. Again we resumed back. So see this, interestingly, this is equal to r square I write. So when I write this, this is the equation of circle. This is an equation of circle. So this is the equation of circle of x minus a square plus y squared equals r square in this form. That means the center of the circle is not at origin, it is shifted to a point A, right? To a point A. So here point A corresponding to I average value. So how do I represent these equations graphically is this way. In this way. So let me have a vertical axis and an horizontal axis. In this axis, let me represent a point M. Point C is the center of the circle, and this point is at a distance from here with an I average value. And this is a center. Let me construct a circle. Let me construct the circle. Not so perfect circle, but it can be considered to be a circle. So this point is C. Now I can represent coordinate M here with ix dash and ix dash y dash. That means what? I would take on my horizontal axis ix dash, iy dash, and so on. My vertical axis, I will take ix dash, y dash above positive, below negative. So product of inertia is on vertical axis, and area of moment of inertia on horizontal axis. If I take, I would have now my m is given by this coordinate, and if I join this cm and then extend this on the other side, I would have this coordinate given by n exactly by iy comma ix dash y dash, where this is minus. So this coordinates I will get. So now, what does this point, if I project this down? So this point is, what is the point corresponding to ix dash? So if I extend this down, so this point is, what is ix dash? Till this point, what do you have is I average. So if this is ix dash and this is I average, so this portion would be ix dash minus I average, right? I average. And this portion would be ix dash y dash. So now you could see this square ix dash minus I average square is what is plus ix dash y dash square is what is this radius r, that is r square. So that's happened to be my circle, right? So you have radius. So I can write this in this way, right? So this is the proof, and this is how I can represent these three equations graphically, and this equation is what is useful to find out the maximum and minimum values of area moment of inertia and so on. So that is simply whatever that this circle intersection with this is corresponds to I max value, and whatever that corresponds to this point is I minimum value. So, and this angle here reflected is 2 theta angle. So 2 theta angle here. So if this 2 theta angle is rotated in the other way, so if I rotate here clockwise direction, this NM diameter, M comes and coincide with point A, and N comes and coincide with point B, where I get A and B by the maximum and minimum values of area moment of inertia. So if I rotate here in this Mohr circle, this by 2 theta clockwise, my section here also should be rotated by the same. So I should rotate my rectangular section by that same angle. Or in this case, some arbitrary section that we have, so that should be rotated by an angle theta to have my x dash y dash to get my I max and I minimum value, right? So you can also look at what is the orientation to be rotated from this trigonometric term. So here this 2 theta is what, tan 2 theta is what is, tan 2 theta is what is Ix dash y dash by Ix dash minus I average, right? So you can rewrite this to be Ix dash minus I average here, or you want to represent in terms of Ix, Iy, Ixy, you have to take this. So when you will have your this will be theta 2 theta m rotation on the clockwise direction, I will get maximum. So how do I get is that when Ix dash y dash is equal to 0, when this is equal to 0, I would have my A B point, which is on horizontal. So that would give me tan 2 theta m value equals minus 2 Ixy by Ix minus Iy. So this is how I would get the orientation of my principal axis. So I'll get two values of 2 theta m, which are 180 degrees apart, in this, or theta m is 90 degrees apart in configuration diagram. So principal axes are the one where you have I max and I minimum and product of inertia 0. So that is what I wanted to teach you today. So you would understand what do you mean by principal moment of inertia, what do you mean by product of inertia. We'll solve some sample problems in the class after CAT to find out or use this formula or graphically to solve for some given section. Right. So with that note, I would stop today's class. If we have any doubts, we can ask. Otherwise, we'll end the class for all. So I would stop now recording.